All right, well, good morning or good afternoon, depending on where you're joining us from today. My name is Mike Mazzarese. I'm a senior engineer with AST Environmental based out of Denver. So the presentation today is going to be about 35 minutes. I know you guys are attending more webinars than you ever have in your career. And so we wanted to make this more of a short format. And we're gonna have some Q&A on the back end. So if you'll see, you've got your little question tab there on your menu bar. And so you can submit those. My colleague, Bill Brab, is gonna consolidate them and provide the questions at the end once we wrap up here. And again, this is a short format, so we're not gonna do a deep dive on any real, any aspect of the technology or applications. If you would like to have a longer format or something that's project specific, please reach out to myself or Bob Elliott. You'll have both of those emails here in the presentation. We can go ahead and schedule that with you. All right, so this is our winter series. We did a spring series too. If you're interested, those are all archived on the RPI Trap and Treat website. These will also all be archived shortly after we give them. So we're going to focus on chlorinated solvent remediation using the trap and treat technologies today, so BOS 100 and CAT 100. Next week, we'll follow up with the second part, which is going to focus on petroleum hydrocarbon remediation. Then we'll take a break for the Thanksgiving holiday here in the States, and then pick back up in December with a two-part series on fractured bedrock. First characterization on December 3rd, and then 1 week later on fractured bedrock injections. So it's one of the fastest growing markets for or injection techniques that we're employing here at AST. So we wanted to break that out into two separate topics to give them both justice. And then lastly, we're going to talk about the pre-drill methodology, which I'll touch on here today, but it's basically using direct push techniques to be able to access contaminated intervals that we can't use, where we can't use DPT alone, where you get DPT refusal. If you'd like to sign up for any of these, my last name's Mazzarese, so the email address that I would recommend using is bob@trapandtreat.com. That's a lot easier for you to write down and copy. And email Bob, he'll get you signed up for these. Or again, if you would like a deeper dive on any of these individual technologies, please let us know. So I always like to begin these presentations by just sort of describing the RPI group in a little bit of detail. So RPI, founders of the group, Remediation Products, Inc., based out of Denver, Colorado. It's the company that developed these technologies. And they also operate what we call our project support laboratory, which I'll be referencing here later in the presentation. AST Environmental, the company that I work for, we're tasked with national and international project assessment and design. We're also an installer of the products. We're also in charge of field quality control. And there's our website there if you're interested to learn a little bit more about AST. And the last leg of this stool is our authorized installer network. So around the country and around the world, we've teamed with companies that we trust to put these materials, to implement our designs, and that we trust to implement them properly, right? So if we can all work together to have a great conceptual model and a great design, and if it doesn't go in properly, it's not going to work, right? It's contact is king, and so we only work with authorized companies. And if you'd like a list for those, they're listed on the RPI website. Now I had to laugh. This map actually comes from the spring. I know what you're saying. It's Mike. I've been looking at maps of the United States with shaded states now for the last week plus. I don't want to look at another one, but I assure you this has nothing to do with swing states. These are the states where we've implemented RPI products. New Hampshire actually is added to this list, so this needs to be updated. But we've worked in most of the lower 48 states, Alaska, most of Canada, most of Scandinavia, and then you'll see a list down there at the bottom UK, France, Italy, Australia, South Africa, and Puerto Rico will be next on this list. So it's kind of a summary slide for the presentation. You know, like most of you, I'm sure most of the projects that we work on are going to be the petroleum hydrocarbon or chlorinated solvent. Same here for us. And you know, you get the occasional oddball, but that's the bulk of the work that we do. And as we'll get into, you know, the technologies are activated carbon based. And so the activated carbon gives us a lot of flexibility in the sites we can work on from a contaminant standpoint, but also from a concentration standpoint. So we can work in source areas, and I have here DNAPL being possible. There's an upper limit to every technology. So once we get into a DNAPL or LNAPL situation, those need to be looked at very closely to see if we can work on that site. But NAPL all the way down to say source areas where you don't have NAPL, but you're in the ppm level, all the way down to plume treatment where we're dealing with say maybe low ppm to ppb type concentrations. A lot of times here, we do implement grid where we go in and grid out the whole treatment area, or we install a lot of reactive barrier walls. There was actually one of the spring webinars that I gave was focused on PRBs. If you're interested to learn a little bit more about that, that recording is on the RPI website. And we've been able to achieve MCL level criteria, low ppb criteria using these technologies. And from a geology range, we also have a pretty wide applicability range dealing with your typical overburden your overburden lithologies, clay, silt, sands, gravels. What's going to change there is going to be your design, right? Maybe your injection spacing, your volume. All of those may change depending if you're in a sand site or a clay site, for example. But we work, as I showed before, coast to coast. So we work in all the varied geologies here in the U.S. And then bedrock and pre-drill, I already sort of covered those in a little bit of detail. And again, those are kind of their own breakout webinars here later in the series. So just to review what we call the trap and treat concept. And so intuitively, we're using the activated carbon as the trap component. And so depending on where you are, whether you're at that distal end of the plume or if you're in the source area, it functions a little differently. So if you're at a PRB, down gradient, plume situation, double digit, triple digit ppbs, for example, don't have a lot of sorbed mass, then the carbon's going to function just like it would in a carbon canister that you'd have on the back end of a treatment system, right? And so that's the trap part. We'll get to the treatment here in a minute. But when you're in source areas, it's a little different because most of the mass is in the sorb phase. So how do we get that mass off the sorb phase into the aqueous phase where it can be treated, sorbed onto the carbon, and then subsequently treated when we're discussing trap and treat technologies? And so the only way that we can do that is to disrupt that natural soil to groundwater equilibrium. And so if we've done a good job on the design and on the installation end, we can adsorb what's available. What's available is what's in groundwater, right? And then now you've disrupted that equilibrium, and you're going to get mass starting to desorb back off that soil to be able to reestablish equilibrium. So this is very similar to what we see with chemical oxidation, right? That's what rebound is on chemical oxidation sites. You treat what's available. That oxidant runs its course. It's not active anymore. Now you get desorption off of the sorb phase to reestablish equilibrium. So it's the same concept here. The one comment that I'll make, and I'll probably make it several times here in the presentation, is that if you're trying to meet a soil standard out on your site, we have to really look at that, look at the contaminants, look at KOCs, FOCs, because obviously different contaminants are going to come off easier than others. And so if you've got I know it's not the focus of this presentation, but if you've got a diesel site, for example, when you have a diesel soil goal, diesel range organics can be difficult to desorb off of soil. So, and obviously the soil type is going to play into that as well. And so now to focus a little bit on the degradation mechanisms, and I spend a little bit more time on this on the next slide. But we're using, I like to think of the carbon as sort of like our cell phones, and we can load up different applications onto that. And so we're adding, besides the carbon, we're adding different treatment mechanisms, whether they're abiotic or biotic or a combination. And so we're going to focus on the top two technologies here today, BOSS 100 and CAT 100. The bottom, BOSS 200 and BOSS 200 Plus. I included that here in case you want to review that. Those will be covered in detail next Thursday on the next webinar in the series. But get back up to the top. So BOSS 100 is an activated carbon that's been impregnated with metallic iron. And so you can think of it's reactive iron similar to zero valent iron that's impregnated within the activated carbon. And so it's actually impregnated within the pore structure of the carbon. It's not just ZVI and carbon blended together. It's actually plated, if you will, within the pore structure of the activated carbon. And so you get the beta elimination pathway. So I'm sure most of you are familiar with this if you've used zero valent iron technologies in the past, where we're not using that that classic ERD, reductive dechlorination, single chlorine transfer pathway that you get with just using electron donor and bacteria, for example. We're going through the beta elimination route, so we're taking, say, PCE to dichloroacetylene, ultimately ending up with acetylene and then ethylene. And so the nice thing here, and one of the common applications for BOSS 100 is inside of buildings that have potential vapor intrusion risk because we're not generating vinyl chloride. Theoretically, you're generating a very small amount, but again, with the activated carbon present, we don't actually see that in practice. So from a longevity standpoint, not all of our sites are monitored in perpetuity. So we've got sites where we've got 6+ years of data. Theoretically, similar to zero valent iron, as long as the iron is active, the product will still continue to be effective. And so I put 10+ years. Obviously, it could be something much longer than that. And it's going to be a function of, again, how much iron is present, how much mass is present, how fast is groundwater fluxing through your treatment zone. CAT 100 is a slight variation. It takes BOSS 100 and we add an electron donor, we add some other components, we add some bacteria. And so it's a combined, you get that same abiotic transfer, but then you also get some classic ERD type reactions as well. And so from the proof of concept standpoint for that treatment, one of the questions that we get asked the most, and this could be its own 30-minute presentation. So this would be an example. If you'd like some more detail on any of these bullets, please reach out, let me know, and we can discuss. First off, we're using the laboratory, which we'll be talking about here shortly. We do a lot of our own experiments. We've done a lot of bench testing for clients, for projects. And so when you can control the variables, you can control all the analytes. Obviously, we can sample for everything in the lab and get close to a true mass balance. A lot tougher in the field, obviously, once we start putting things in the ground. And so when we talk about total mass reduction, we're looking at projects where we've got pre and post soil and groundwater data. So here's an example. Now this is a hydrocarbon site. But the same would obviously apply for a chlorinated site where, first thing that I'll draw your attention to is the time frame between the samples. So we're talking about 3.5 years in between these individual soil sampling programs. And so each of these dots represents a soil sample, and the pre in red is what we based our design upon, and the blue was some of the confirmation sampling that was done on the back end as part of the closure process. So we've got this type of information for This was a project in Europe, but we've got sites in the United States as well, where we look at, again, pre and post total mass in, total mass out. You can also look at long-term groundwater data. This is that same site, again, looking at benzene. For this particular project, this site also had actually twice, because of some regrading that had to be done, the wells were replaced actually twice out on this site to make sure we've got a representative groundwater sample. And we can see long-term data here, 5 years of groundwater data, as well as the replacement wells, as I mentioned. So chlorinated solvents, to go back to chlorinateds, we have the advantage of having dissolved gases and daughter products that we can actually look for. Hydrocarbons are always a little more challenging. We'll talk about that next week. But on chlorinated side, we can look at dissolved gases like acetylene, which I mentioned on the previous slide as being generated via the beta elimination pathway. Also look at ethylene. We can look at things like chloride to be able to track and make sure that we're getting complete treatment. We can also look at microbial diagnostics, and so we can look at things like DHC, dihalococoides. We can look at functional genes being generated. I'll actually give you a little deeper dive on this particular project later in the presentation. And then lastly, not being used as much is CSIA, where whenever using compound isotope analysis, excuse me, to be able to make sure that we're getting true biodegradation out on these sites and not just sorption. Because if you're just changing the phase of the contaminant onto the carbon and you're not getting degradation, you're not going to disrupt or you're not going to alter that del ratio. Okay, so I like to say that everything works in a beaker, and one of my comments I hear often talking to clients about different technologies is that didn't work. Well, that's not really true. It probably, all these technologies, ours and the others that are in the market, they're all developed in the laboratory, and they do work. So why do they work in the lab and they don't work in the field? And most of the time, it comes down to really two things. It's either loading or distribution. And to spend a few minutes on that loading question, especially talking about source areas, what gets underestimated in my opinion, often is that sorbed mass component. We often don't have enough soil data to be able to really develop a really tight CSM, or it might be just sparse, or it might be old, or both. And so soil is really what we really hone in on when we are looking at source area designs. And this is where the RPI lab comes in. So this image that you see on the left there is an image that a client of ours generated. Each of those spheres is a soil sample. So they're generating 3D images like you would see with, say, like a high-res technology like the MIP or the LIF, but we're actually generating these types of models, quantitative models, using soil data. So we call that process the RDC, or the remedial design characterization. And it's a collaborative process that we work with our clients, consultants, to be able to review the current CSM and see if we can leverage the laboratory to fill some of those data gaps and really fine tune the CSM. And just to give you some general terms, in general, we're profiling soil every 1 to 2 feet vertically down through the saturated zone. And if we've got that long groundwater screen, like if we've got a 20-foot saturated screen, maybe we're doing some either nested implants, or we're grabbing some temporary groundwater samples as well. And this process, the RDC process, was recognized in the recent ITRC guidance document. If you'd like a link for that, please let me know, or you can just go to the ITRC website. I'm sure it's easy to find. And the thing about the RPI laboratory is that they run their analyses pro bono. It's not certified in any state. It's just for design purposes, but you're getting 8260B data and other common EPA methods. I already showed you that figure, and so we take that information and we carve up the site into all these different air treatment areas. And each of these areas that is broken down they're broken down vertically as well. So you may have a shallow, intermediate, and deep interval, depending again where the mass is. And so this optimization process almost always pays for that upfront additional characterization work. I go back here to this. This is a site that I've been involved with that's up in the Pacific Northwest. It's happens to be a carbon TET site where BOSS 100 was applied. And they collected 91 soil samples, I believe, out of these borings in one day. Now, it was a big effort. It was probably a 12-hour day out in the field, but in one day, they were able to generate 91 soil samples, and it really helped us. It really changed the model for this site, and really shifted the way that we ultimately ended up designing and implementing the work. So here's just a quick rundown of the capabilities of the laboratory or the equipment that they have. If you'd like more information on the laboratory specifically, please let me know. So here's just an example of a very large scale. This is our largest scale RDC, I think, that AST has implemented. So this is not your average site, obviously. We work all the way down to corner gas stations, small dry cleaners, where maybe you're advancing 5 soil borings, sending 30, 40 soil samples to RPI. Well, this is on the other end of that. So almost 80 soil borings were advanced, over 1,100 soil samples collected, 46 nested groundwater clusters were installed as well, with 142 individual wells. And so all what you see, all that soil and groundwater was sent to the RPI lab, and it was all run at no cost to the project. And so they were able to generate these heat maps here for soil and groundwater based on this information. All right, so I'm just gonna spend one slide on application techniques. So direct push, I think it's best practice to always inject top down. That's probably a discussion if you want to, again, reach out to me. I can kind of dive into that a little deeper, but we think it's best practice to always use top down techniques. Really, for any injectate, I think it's really more important. It's critical for when you're injecting slurries in any of those geologies that I have listed. So that pre-drill that I had talked about before, and that's the focal point of webinar 6, we're using that to get through, in situations where we've got weathered bedrock or glacial till. So in the Pacific Northwest or Canada or in the Northeast US, where we've got a lot of till, a lot of glacial till geologies, we can use this technique, again, weathered bedrock, or if it's fill material. We had a site in New York City, for example, where we're dealing with fill material. And we're using, talk about bedrock, webinars 4 and 5 will discuss this specifically. 4 is characterization, 5 is actually injection. And we're using straddle packers, custom built straddle packers. And I think I have a picture of those here to be able to isolate fractures and pressure inject the BOSS products. And then lastly, if you ever have access to be able to soil mix really any technology in, and so ours fit into that. Anytime you can direct mix it in with either installing a trench like what you see here, this was a site in Pennsylvania that I worked on, or if you were doing an excavation and you want to mix in one of these technologies into the smear zone, you'll never get better distribution than that. And so it's something that I always recommend looking at if it's available to you. Okay, so we're about 25 minutes in right now. So we're gonna spend about 10 minutes going through some project summaries. All these summaries are broken out and we have full write-ups on them. Obviously from a time standpoint, I can't go into each of these in tremendous detail. So if you're interested, you can either visit the RPI website, AST website, or just reach out to me. So we'll start first with a site that's got pretty high concentrations, suspected DNAPL. So this was a former Atlas missile site in the Midwest. And as you'll see, pretty high concentrations of TCE and groundwater, really around one well. And so this was a pilot test to be able to see if the BOST 100 technology could handle these concentrations and also get distributed in the subsurface. So there was a perched groundwater table at around 50 feet BGS. It was a low plasticity clay till that we were injecting into, and this actually was a pre-drill site. So we did have shallow DPT refusal, and so augers were used to advance down to the bottom of our treatment interval. And then we was backfilled with hydrated bentonite, and then re-drilled with direct leach. So the RDC portion for this, we had 5 locations. So we had 4 monitoring wells and 1 CMT well, or multi-channel well, where we had 7 channels between 22 and 70 feet BGS. And each of these locations, soil was sampled approximately every 2 feet, with a total of 115 soil samples coming to the RPI laboratory. So we ultimately went with 21 injection points out on the site, and I already discussed the need to use the pre-drill methodology using hollow stem augers. So we had 14 of these injection points that were advanced to 70 feet BGS and 7 to 54, and we ended up using different spacings out on the site, mainly based on the concentrations that were observed during the RDC. And about 7,500 pounds of BOST 100 was applied back in 2016. And so this project, here's the data that we have to date. MW18 was our target well within the pilot test area. And there was you'll see there's a long gap between sampling there, and that was the pilot test scope of work had run out back in 2016, and so it wasn't sampled until late 2019. But you can see our TCE concentration reduced 99+% at 1,300 days. And so this is a good example of, even though it's a small project, it's one site, that over time the technology can handle these higher concentrations. MW27 and 28 are side gradient, and so you can see the decreases that were observed, not as great as MW18, but these were outside of the treatment area. Secondly, we'll talk about a site kind of on the opposite end from the concentration standpoint. Relatively low, or 200 ppb PCE, was discharging into a creek at a site in North Carolina. And so back in 2013, a pilot test was performed, and then 2 rounds of full scale were completed in 2015 and 16, and it's currently in long-term monitoring. One thing that's interesting about this site, or unique, excuse me, is that each of the injection points were angle drilled underneath the creek. And that's, if you look here at the map that was provided by our client, you can see that they had a series of well clusters on either side of the creek, and they were able to show through their well network that the PCE was diving down into this weathered rock and then ultimately discharging into this gaining creek. And so we were tasked with sitting up on top of the creek bank and angle injecting underneath to try to cut off the PCE discharging into that creek. So here's this is what the pilot test looked like. So it was a 60-foot section. So those injection points are on 5-foot centers. And you can see there in cross section, our client generated this map. Each of these hash marks represents a successful interval. And you'll see there are some gaps here. And so that means that maybe we had a little bit of surfacing, or the injection tool clogged, for example. And so we didn't get the whole design volume in. And that's just field work, that's injection work, right? You have to have a high density of points to be able to account for those types of issues in the field that are going to be that we all encounter on any of our injection projects. And that's really what gets to the reason behind us having a high density of points, multiple rows of points whenever we do PRB designs. So these were all completed 25 degrees from vertical, from 8 to 35 feet BGS. And here's data for this site that I have to date. And so the monitoring points for this well, or for this site, are stream bed piezometers. So PZ103, PZ101 are the two wells that were monitored long term. As you can see, once we got to about 189 days into the project, we've been below 5 ppb and have met the objectives. So we've got about 5 minutes. We'll talk about a CAP project here, and then we'll open it up for some Q&A. So this site had very high concentrations, so it necessitated us to switch the technologies from BOSS to CAT 100. And there were multiple degreasing areas, scrap handling area, drum storage area, so kind of your typical manufacturing site chlorinated source areas. So this was our initial injection area out on the site, about 4,000 square feet, with a treatment interval between approximately 9 and 32 feet BGS. And so MW71, the one there that's inside the building that you see, is the one that I'll show you the data from. And so here's these are the molar plots, stack plots. And so as you can see, when we're starting here, you can see the amount that's in TCE, very little cis, really no vinyl chloride, no ethylene. And so as you can see here, we're talking about 2015. So this project's been in the ground for quite a while now. I don't have any 2020 data currently, but you can see what you would, more of a classic ERD response out on this relative to what you would see on a BOSS 100 site, where we see our TCE dropping down. Then we have our DCE being generated, vinyl chloride following, and that's been really the majority of the project has been dealing with this DCE and vinyl chloride, but we are finally starting to see that come down to where we have very little cis, some vinyl, but we have continued strong ethylene generation with one application of the technology back in 2015. And so here's that. I mentioned chloride as being one of the indicator parameters that we can look for. This is really applicable for like DNAPL or high concentration sites. Most low concentration sites, you're not generating enough chloride to be able to distinguish that concentration increase. So really, this is something that we look for on more higher concentration sites. Same thing with ethylene and acetylene as well. And I mentioned the microbial diagnostics data. So on this site, they've been monitoring really since the beginning. December of 15 was baseline samples. And so you can see here that's this light blue. Really low population, 1 × 10⁻² cells per mil for DCE, and ideally you're up in this 10⁴ range, which we've been able to sustain since we did the application. And you also see here are your functional genes, your TCE reductase, here are your VC reductase functional genes that we've been able to, at baseline, really were non-detect, and we've been able to increase their concentration and be able to keep that elevated. And that's really, I think, it indicates to us that we're that the product is still working, and that's after, again, one application 5 years ago. Okay, so that's 35 minutes on the dot as promised, and so I'll open it up now. I guess, Bill, if you don't mind unmuting yourself, and we can dive into some questions.
Yeah, Mike, thanks for a great presentation, and thank you to everybody that has attended and stuck to the call so far. Mike's going to field some questions that have come up in the Q&A section of the platform here. If we don't get to your question, we will follow up separately offline via email or other means of contact with you accordingly. So, Mike, we got a few questions here we can go over. First one that came up in here was an interesting one. Earlier in the conversation and presentation, you had shown some longer-term data involving the petroleum site with the benzene, where you had soil and groundwater. And the question that's come up here is that the benzene being a mobile and compound in most porous media, how did the data from that site support the remediation over 3 years rather than it migrating away? Can you comment on that a little bit?
So if I understand that, is the question referring to pushing the contamination outside of the treatment area? Is that?
Yeah, that's how I'm reading it, or that it's migrated out of the area. Are there other points that would maybe suggest that it's under control?
Right. I mean, obviously, I only showed 2 wells there, and the wells on that particular site, obviously, there's quite a large well network, and that's really all of our sites that we work on, where we've got down gradient compliance and sentinel wells. Sometimes we have to install wells, or if that gap is too big, maybe we're actually installing wells in between. But we don't see pushing contamination. First off, I guess whenever we're talking about, to get into some detail on the actual field work, we're always working outside in. Okay, so when we're out on a site and we're working on the periphery or the down gradient edge, we're working on the outside in to the extent that we can, so that if that even was a possibility of happening, it's going through reactive media. But the other thing to keep in mind is when you're talking about pore volumes and how much we actually inject in the subsurface, it's a relatively small volume of the overall pore volume. So it's not like a high volume injection like you would typically see with, say, like an ERD technology like EVO, or say chemical oxidation, where you're trying to fill up a certain percentage of the pore volume. And in that case, I've seen sites where that has happened. But with slurry injections, the volumes are relatively low. And so we didn't see on that site, or really on most of our sites, or sites that I've worked, that I work on, where we see where we've displaced contaminants and now we've pushed it outside of the treatment area. So I hope does that answer the question, Bill, do you think?
Yes, I believe that covers it based on the way I'm reading it. If not, we can follow up separately and take care of that. Yes, the attendee that asked that question said that answers his question. So thank you much.
Great. Thank you. Great question.
All right. Another question here in the chat pertains to the modeling imagery that you showed. I know there were several images of 3D models that were utilized in the presentation. Would you care to comment on the question is specifically which modeling package was used for those pieces of data that you showed?
One I know, one I don't know. The first one, which was the yellow yellow model, that was the carbon tetrachloride site. That was either EVS or MVS, and that was done by our client. The second package, for the site, the Ann Arbor site, I'm not familiar, but we can get that information and circle back with you.
Great. Great. And then moving on to some questions related to the actual installation methodology. There was quite a bit of information covered as far as how the materials and technology is implemented, many different regimes of installation. Would you care to expand on some of those a little bit and talk a little bit about the different geological regimes that we'll be working within?
Right. So I guess I guess specifically, I guess maybe just we can focus on, overburden for just a few minutes, because obviously bedrock is kind of a separate animal, and that has its own separate webinar series. But talk about overburden a little bit. And so, I guess, Bill, you're referring to just, like basically how we go about doing this work. Is that
Yes, there's a couple questions about it in here, but yeah, it's mainly the common theme is methodology of installation, and
Sure.
overburden,
Yeah.
I think is where most of these are steering towards.
Cool. All right. Yeah, no problem. So, in general, our application patterns are going to be either in a grid or in a PRB. So the PRB I showed here, so you get back here. So this is kind of what a typical PRB layout looks like. And I would say the injection point spacing is pretty tight, usually 5 foot on center to maybe 7.5. It's gonna be a function of depth. And so injection point spacing is, 5 to 10 feet for most sites. And that's going to be a function of the geology, starting depth below grade. Because as your injection spacing widens, your injectate volume has to increase accordingly, right, to meet the rates of influence that you need to match up with the adjacent location. So when you're working at, say, 5 feet below grade and you're at an active gas station, for example, because gas stations are good examples because they've usually had historic digs. They've had a lot of investigation work. There's tanks, obviously dispensers. And so there's a lot of things to work around. And if your groundwater is at 5 feet below grade and you try to inject on a 10-foot spacing, a slurry on a 10-foot spacing, you're going to have a mess because you got to put quite a lot of volume in to be able to hit that ROI and so on. In that situation, we would default to a much tighter spacing, probably something on that 5 foot end, the 5 foot range. Then as you go deeper and so if you're working at 20 feet below grade, or deeper, that spacing is going to increase 7.5, 10 feet. Now we do have the injection system that we use for our bedrock sites, has pretty high flow capacity, up to 300 gallons a minute. And so we have used that selectively on some overburden sites where we are working deep and we can really push the radius of influence. So maybe you can, in that extreme case, if you're bringing that unit out, maybe you're working on a 15-foot spacing. But in general, we're on that 5 to 10 foot range. And the injection volumes are going to vary depending on the geology. So if you're working in a clay or a silt and you're on that 5 foot spacing, you might be working in 10, 12, maybe 15 gallons per interval. And those intervals are going to be spaced vertically, say 1.5 to 2 feet vertically. And as that injection spacing increases, assuming you have a site where groundwater is deeper, if you're in that 10-foot spacing, maybe you're in the 40, 50, 60 gallon range of slurry. And so those are injected at relatively high flow rates. The pumps we use are positive displacement, so it's whatever pressure is needed to meet that flow rate. And so pressures are obviously going to vary quite a bit. The systems that AST uses on most sites, the injection systems are capable of injecting up, they max out at 1200 PSI. That's system pressure, not downhole pressure. Downhole pressures in general are going to vary, say, between 50 and 500 PSI, I would say, for most sites, once you peel out the system losses. Other sites, more, bedrock and things like that, pressures can be a little bit higher. So I don't know, Bill, I know that's a lot of information. I don't know if there's anything that you want to add to that, maybe if there's any gaps things that I left out.
No, I think you covered everything fairly detailed. One follow-up question that did come through during your answer to that question relates to injecting through existing injection wells on the site. We cannot inject through existing cased wells when we're talking about overburden or even consolidated lithologies because we are injecting solid particles. Essentially, just trying to install through a cased well is going to get caught by the filter pack and or fill the casing that's existing there. So all the points that Mike has talked about here in the overburden scenario are temporary dedicated points. And if we're working in consolidated lithology, we do need to have open boreholes. Again, we'll get into that in more detail with the 2 follow-up presentations in a couple weeks on the bedrock installation. So unless you want to add anything else to that comment, Mike, I can move on to the next question here.
Yeah, no, go ahead. I think we're good.
So another question that came through in the Q&A is, are we using an on-site lab for such intense analysis? And what are your thoughts on using a MIP versus multiple grab samples? It's definitely getting to the laboratory question and using integrating HRSC into the work here.
Yeah, we've talked about using like those little frog units that I'm sure you've seen it. Maybe some of you have used them. We've talked about that. I'd kind of love to get one of those out on one of our sites, but haven't used any sort of on-site lab. And we certainly could, but we haven't to date. I mean, but I'll give you an example of where using the fixed lab that's in Denver was used in real time. So I was installing a PRB recently up in the Northeast, and as we were installing the PRB, we were installing quality control wells. And so we would finish a 40-foot section of the PRB, install a well on the down gradient side, sample it, and keep going. And then we would overnight those to the RPI lab. I would have analyses the next day, letting us know whether or not we had to come back and retreat an area or if we needed to make any tweaks to the design. And so we have used the RPI lab in sort of that same sense to get some real-time monitoring, or close to real-time monitoring, to be able to make real-time field changes. And then to answer the question about the high res, my previous company, I worked with high res for close to 8 years, everything from the MIP, HPT, UVOST, and I think they're great technologies. They have a purpose, right? So they help us identify extent, vertical, lateral extent, but they don't provide quantitative information. So you can't tell me if you're getting an ECD or XSD response or a PID response, that equals X micrograms per liter of PCE in groundwater or soil, right? And so we always have to back up those surveys with a good amount of soil sampling. Now, if you're going out with those technologies on the front end, you can certainly optimize that RDC process that I had covered today. And so, we know that, okay, we only, the plume is this size. We've defined that. Now we're going to go out, we're going to get our soil and groundwater data to be able to, use that in combination with the high-res information, especially that HPT. HPT is a critical tool, I think, whenever you're doing PRB designs, because it really helps you ID where those transmissive zones are. You can sample those, and it really gives you really good mass flux measurements or calculations. And so definitely integrate those tools, but if you're going to go out and use them and you're thinking about using the BOSS technologies or the RDC process, reach out to me or one of our other project managers, and we can give you an idea on, the amount of samples that we would like to see. The one thing that I've seen most common are really 2 things. One is little to no confirmation sampling is done, and we get that data set, and we can't do anything with it. I mean, it helps us understand kind of where things are, but it doesn't provide quantitative, it doesn't give us mass, right? The other thing is just, where you've got a very limited number of samples and you're trying to correlate that data. It's really difficult to do on most sites. And I think the folks that work with those tools every day would tell you the same thing, that you've got to, it's really hard to correlate. You got to kind of run those paths in separate, and then you can draw some correlations, I think, if you have a dense enough data set, but you can't go out on a site where you've done 2 weeks of MIP and grab grab 3 soil cores and a couple grab groundwater samples and expect to correlate that and come up with a remedial design.
Yeah, and I just want to add to that, Mike. Going back to the laboratory discussion, I've also looked at using the frog tool before and having a third-party mobile laboratory come into overlap on the sampling effort in the field before, and time and cost-wise, it is more effective that we've seen in doing a cost comparison to actually just sending the samples off. One, on a cost issue, but also on the level of interrogation that the RPI lab can perform on the samples that are being sent in-house for that purpose. So whereas in the field, if you're using a field instrument, whether it be a laboratory or the handheld frog unit, your potential downtime with dealing with higher mass zones can be prohibitive to the total effort at the facility. Whereas if you're logging and containerizing samples and sending them off right away, we've been free to keep on moving forward. And then looking at the overlapping of the high res along with the lab analytical, just like Mike said, very, very well phrased and covered here, is that qualitative versus quantitative aspect. It is becoming more popular on my side here locally with the regulatory body and private clients of integrating the HRSC as part of the RDC to guide the sampling plan in real time. So with the HRSC data, you can get a pretty good idea of how the site contaminant mass is distributed, both spatially, vertically, and horizontally, and it helps to guide where you want to take your confirmation samples. And so I've been involved in several sites over the last 18 months, 2 years, where the programs have bought into the idea of using this HRSC to guide a follow-up sampling plan in relatively short order, talking like weeks as opposed to months and even years in some cases, as we've seen in the past. So quite valuable for us to utilize the tools as they're meant to be used as a total package for determining where we need to go, and then using the sampling to show the quantitative measure of what's present in the subsurface.
Yeah, I guess just to add one thing, Bill. So we've got, I mentioned myself, Ed Creedon, who recently joined AST from Dakota Technologies, is also obviously, if you're familiar with that company, intimately familiar with all of the high res tools. And so we've got folks on our side that are used to using that data. And again, we're fans of the technology. We just want to make sure that you've got the proper sampling plan on the back end to be able to give us the information we need to ultimately give you a design.
Mike, I know we're approaching the hour time frame here. There is one final question I think that could wrap us up with related to the lab and what we've been talking about on the sampling side. Can you go into a little bit of discussion about the lab cost or cost associated with this type of work? I know you covered the pro bono part of the analysis, but could we talk a little bit about how that would affect a total cost of a project? Does that make sense, what I'm asking?
No, I guess I don't understand. I mean, there's no, basically the costs that are not covered, maybe this answers it to a certain degree, and Bill, you can kind of add on if it doesn't. Obviously what's not covered is the collection and the shipping, glassware, all of that is not covered by RPI. Once the samples get to the laboratory, the analyses are performed pro bono. Now, I did mention just one little side note. I mentioned some bench scale testing that we've done for clients. That is not pro bono. So just to make that note. But the analytical soil and groundwater are. And so I guess, Bill, when you're, I don't know if that answers the question at all, or if you want to add on to it.
Yeah, as far as I'm reading the question, it's just asking what the charge per soil sample is, and so I wanted to get into a discussion of that just a little bit to wrap up. That yes, the analysis as you covered for any of the samples submitted are covered at no cost. However, the part that obviously is required for consideration on costing is what it takes to actually obtain that sample and get it to the laboratory. So I just wanted to clarify that as responding to that question. I hope that answers the question for the individual that asked that. But if we're just talking strictly about the analysis itself is performed pro bono as part of the package.
Right, and I guess just the one thing that we didn't mention, or I'll mention it again, is that the lab supports you on the back end of a project too. And so, we've spent most of the time talking about the upfront design support, to help to fine tune the CSM and develop a design. But RPI also, the laboratory runs very specific analyses that relate to these technologies. And so, for example, besides dissolved gases, so looking at things like acetylene and ethylene, or volatile fatty acids, anions, so sulfate, nitrate, the additives that are included with BOS 200, or chloride. So you get a pretty long suite of analyses that are specific to these technologies that we cover today and we'll cover next week. And so it's, as part of that effort, we grab groundwaters as part of the baseline too, make sure we have baseline values for all those constituents. And as often as you want to send groundwater samples to the RPI lab, they will run them post project as well.
Yes, that answered the question as responded here in the Q&A here.
Awesome. Well, we're up against the hour. Thank you all so much for attending. If you would like a copy of the presentation, or again, the recording will be on the RPI website shortly, within the next few days or a week. And I hope that you're able to join us for some of our subsequent webinars. All right. So have a great day, everyone. Stay safe and sane.